So that was a lot of work in our previous video to analyze the case where we had complex and distinct poles. So what we want to be able to do is make a generalized equation for this case. So let's consider some f of s which has complex conjugate poles. So it's then going to have related terms in our partial fraction expansion that look like this below. We'll have k divided by s plus alpha minus j beta plus our k star divided by s plus alpha plus j beta. And so this star notation indicates that this k star is a complex conjugate of k. And so to write that out more clearly, we can say that our k is equal to the magnitude of k, angle theta. We could also write that as magnitude of k times e to the j theta. So then our complex conjugate of k, k star, is going to be equal to the magnitude of k, angle negative theta, which we could also write as magnitude of k times e to the minus j theta. And so what we're interested in then is how do we take the inverse Laplace transform of this. So what we want to know is how can we take our inverse Laplace transform of this function here, because we don't want to have to go through that same process that we went through in the previous video every time we come across this. And so simplifying that process, we can say that it is equal to, the inverse Laplace transform is equal to 2 times the magnitude of k, e to the minus alpha t times cosine of beta t plus theta, and then all of that is multiplied by our unit step function u of t. So this is our generalization for our distinct and complex poles. So one thing to note is that this k term is related to a specific pole, so we can't just choose either one to be our k. So let's note that explicitly here. So our k coefficient is corresponding to a particular pole, so it corresponds to our s plus alpha minus j beta pole. And so what that means is if we mix up k and k star, we're going to have the incorrect theta value here. So if you go back and you look at the example from our previous video, so for our previous example, what you could see is that our theta in that case was equal to negative 53.13 degrees. And so it might be a good idea to go back and look at that example and see if you can use this general form to get our inverse Laplace transform a little bit easier. So as I've said in a couple other places, there is also a case 4. So case 4 is when we have complex and repeated roots, or complex and repeated poles, rather, of our f of s. And so we're not going to cover this in this class, but we'd basically just do it the same way that we did for case 2. We just have complex math. So I imagine everybody's very disappointed that we don't get to do our repeated case, which was already a little lengthy, with complex math thrown in. But hopefully our next topic of convolution will cheer you right up.